Welcome to section 10.6, Random Variables and Binomial Distributions. In this lesson, you will learn what a random variable is, what probability distribution is and how to interpret one, what a probability histogram is and how to interpret one, and how to interpret a specific kind of probability distribution, the binomial distribution. Let us begin by defining random variables. Unlike the variables you've studied in the past, random variables take on values based on the outcomes of random events. An example of a random variable x, and notice I'm using a capital X here, is where x is the result of rolling a six-sided dice. So instead of saying x is a number, x is a possibility of an outcome. So x could take on any of the values in the set 1 through 6. An observed value, lowercase x, of a random variable is only known once the random event actually occurs. So in the example above, lowercase x would be 3 if you'd rolled a 3 on the dice. But until you roll it, you don't know what the value is. So unlike a regular function where you say, oh, well, x is 5, so f of x must be 7 because, whatever the equation is that you're using gives you a specific value. In the case of a random variable, it's simply the result of a random event. Probability distributions and histograms. A probability distribution is a function that takes each possible outcome of a random event, or we could say each possible value of a random variable, and then it calculates the probability of that event occurring. A probability histogram is simply a type of graph that displays the distribution function. In fact, it's a histogram, which you might remember making sometime in one of your previous math classes. The sum of all the probabilities in this probability distribution must equal 1. So in other words, you calculate the probability of one thing happening, you calculate the probability of another thing happening, and you calculate the probability of all the possible things that could happen. And when you add up those probabilities, they have to equal 1 because something has to happen. It might make more sense once we actually start drawing some of these histograms. So let's just go ahead and start working. In example 1, this graph here with the little bars on it is a probability histogram. In this probability histogram, we're looking at the sum of two dice that we roll. And notice that it starts at 2, that's the lowest value, and it goes up to 8. So these must be unusual dice, and in fact they are. If we look at this picture over here, these are the dice that we use to make this histogram. These are four-sided dice. So what might be of interest to you is that while the six-sided dice that we see in most board games is definitely the most common kind of dice that there is, there are close to dozens of different kinds of dice out there. The four-sided die is a tetrahedra, or a tetrahedron. Tetrahedra would be plural. So these two four-sided dice are tetrahedra, which is a geometric name, and in fact most of the dice that we deal with have geometric properties to them. And if we really wanted to talk about the math of how you actually build dice like this, we could get into that if you're ever interested. You'd probably want to give me a little bit of heads up so that I could refresh myself on the math, but we could certainly talk about it together at some point, although it doesn't really have any bearing on this class right now. I've made a little table down here. So the top row are the numbers that you could roll on the first dice, and the bottom row are numbers that you could roll on the second dice, and between them I've gotten all the possible different combinations that you could roll. Now, how many are there? Well, fundamental counting principle here. So there's 4 sides on each dice and you're rolling the 2 dice. So that's going to be 4 times 4 different possibilities, or 16 different possible ways you could combine those rolls. And that's what this table here displays. So I'm going to ask, what's the probability of rolling a 5? Well, the first thing we need to do is go through and find ways that you could roll a 5. So let's do that. Well, 1 plus 4 is 5. So there's one of them. A 2 plus 3, that's 5. 3 plus 2, that's 5. 4 plus 1, that's 5. Are there others? No, there aren't. We could search through them, but there aren't. So, what's the probability of rolling a 5? Well, there's 16 possibilities. They're all equally likely. And 4 of them roll a 5. So that must mean there's 4 out of 16 ways to roll a 5. And 4 out of 16 is 1/4. And if you put 1/4 into your calculator and turn it into a decimal, you get 0.25. Let's look back at our histogram. The possibility of rolling a 5 is 0.25. So this is how you read the probability histogram. You look at the outcome that you're interested in, you go up to the top and read across, and that value right here is the probability of that event occurring. So, alright, what's the probability of rolling at least a 7? Well, we can again look back through the outcomes that we have here. Which ones add up to at least a 7? No. 3 plus 4 is a 7. 4 plus 3 is a 7. 4 plus 4 is an 8, so those all count. So that's 3/16. 3 divided by 16, we get 0.1875. That would be the same as taking this chunk here, adding this chunk to it. So let's kind of draw that on top there. And going over, and there it is, 0.1875. 187, I'll just do 1.87, that's close enough. One more thing we should mention about the probability histogram is we just want to verify that the probabilities of these events, when you add them all up, that gives you 1. And so I know that this one here is 0.875, and I also know that when I add these two together, I get 0.875. And in fact, if we look at this histogram, I can see that this is as tall as that. In other words, the probability of getting a 3 is the same as the probability of getting a 7. And the probability of getting a 2 is the same as the probability of getting an 8. So I can lump these guys together with these guys, and I know that that's 0.875, so that must be 0.1875. If I put those together, or in other words multiply that by 2, I get 0.375, the stuff that I've shaded in already. And then I actually know that these are 0.875 as well. I can figure that out by saying what's the probability of rolling a 6? Well, that's 2 plus 4, there's one of them. Or 3 plus 3, there's another one of them. Or 4 plus 2, there's one of them. And that's it. 2 plus 4, 4 plus 2, and 3 plus 3. That's 3/16 also. So in other words, this is 0.1875. And this is 0.1875, and so I'm going to have another 0.375 from those two. And then finally, we calculated already that this was 0.25. On my calculator, I'm going to add plus 0.375 for the other one, plus 0.25, and my answer is 1. And adding that final 0.25, that was all of the probabilities. We've added them all up now. So I just wanted to show that that was the case, and it has to be the case in a probability histogram. So let's talk about the binomial distribution. The binomial distribution is a probability distribution. However, it's a probability distribution that has very specific extra criteria involved in order to be called a binomial distribution. And these criteria are as follows. There must be n independent trials or events. So in other words, you have to compute a random variable n times, and the random variables have to be independent of one another. In other words, the result of one cannot depend on the result of another. Also, each event has only 2 possible outcomes. And we'll just call them success or failure to be generic about it. Or we could say yes or no, it doesn't really matter. They just have to be two distinct possible outcomes. Also, the probability of a success must be the same in each trial. And we're going to call this probability P for the sake of our formula. Well, if the probability of one outcome is P, and the two probabilities either of success or failure have to add up to 1, then the probability of failure has to be 1 minus P, which is the complement of P. So, given all these conditions, we can say that out of n trials, the probability of k successes is this nice, long, messy, horrible formula here. But we can use this formula to produce a probability distribution for a binomial distribution. Let's do that now. Example 2. Skittles again. So, suppose you have a bag of Skittles, and 30% of them are red. Suppose you reach into the bag and you pull out a Skittle, you write down whether or not it was red, and you put it back in the bag. And let's say you do this 6 times. So when you're done, you total up the number of times you drew a red Skittle. So what we're going to do is we're going to construct... Now, I wrote a binomial histogram here, and I could have written a probability histogram. I guess what I'd like to say is, think about our conditions here and verify with what we know about binomial distributions that what we have is actually the conditions necessary for a binomial distribution. So, what we're doing is we're performing trials. We're pulling into the bag, getting a Skittle out, and looking at it. And then the outcome of our trial, there's only 2 possibilities. Either it's red or it's not. In other words, either we have success or we have failure. Also, since I'm putting the Skittle back in the bag, that means that these are independent events, because each time I reach in there, the result is not affected by what I did last time. In other words, the events are not dependent on one another. The proportion of Skittles in the bag will always be the same, because I'm not eating the Skittle, I'm not changing the numbers of red in the bag. And so that really covers our bases for this being a binomial distribution. It's independent events, we're drawing multiple times, and the events are either a yes, it was a red Skittle, or no, it was not. There's 2 possible outcomes. Okay. So let's actually try to construct this. Well, alright. So here's the thing we need to know. What is P? P is the probability of drawing a red Skittle. What do we know about the Skittles? 30% of them are red. So what does P mean? P is going to be equal to 0.3, which is the same as 30%. What are our n and our k? Those are the other variables in the formula. Well, n is the number of times that we draw the Skittle out of the bag and record it. That's our number of our trials. How many times do we do that? We did that 6 times. And what's k? K is the number of red Skittles that we drew out of those 6 trials. So in this case, k can be anywhere between 1 and 6. So k is in the set 1, 2, 3, 4, 5, 6. And actually 0's in there too. I should have listed that. Right? We could draw no red Skittles on any of the times we reach in there. Or we could draw anywhere from 1 to 6. Okay. So let's actually calculate these things. So how many ways out of 6 could we choose 0? That's going to be 6, choose 0. And then we've got P is 0.3. And then we're going to take that to the 0th power because we're going to start off by choosing k equals 0. And we're going to multiply that by 1 minus p to the n, that's 6, minus 0. Alright. Well, let's 6 choose 0. How many ways can I choose nothing? I think we've sort of defined this as being 1. What's 0.3 to the 0th? Well, anything to the 0th power is 1. I put p here. I really should put 0.3. What's 1 minus 0.3? That's 0.7. 0.7, 6 minus 0 is 6 to the 6th. So, we're going to have 0.7 to the 6th is 0.117, or 0.118 to round up. 1 times that is still 0.118. Over here, I think it might make sense just to sort of draw some things in here. I'm going to call this 0.1, and I'll call this 0.2, and I'll call this 0.3, and I'll call this 0.4, and I don't think I've got to go much higher than that, but that's just personal experience talking. Alright, and so now I'm going to get myself a little rectangle and throw that on there. So 0.118, that's about right there, I'd say. And so this, right here that I've drawn, that's the probability of drawing no red Skittles. Alright, so let's go on and do the next one. What's the probability of drawing 1 red Skittle? Well, that's when k is 1. So I'm going to go 6, choose 1, times 0.3 to the first power, times 0.7, that's 1 minus p again, to the 6 minus, and now k is 1, so 6 minus 1. Okay, so let's do that on our calculator. Alright, so 6 math, probability, choose 1, alright, is 6. And now, I'll write that here, so that's 6. 0.3 to the first power is just 0.3, so that's times 0.3 times, now 6 minus 1 is 5, so that's going to be 0.7 to the fifth power. Alright, so what do I have there? It's 0.168. I'm just going to do 0.17, that's okay. So what does 0.17 look like? Well, let's add that on there. That's the probability of drawing 1 red Skittle. And we can keep going with this. And we're going to do k equals 2 now. So when I do k equals 2, I'll do 6, choose 2, times 0.3 to the second power, because k is 2, times 0.7 to the 6 minus 2 is 4. And when I do that, I get 0.32. There we are. That's 0.32. Okay, great. And we can keep doing this. Actually, it would be really good if you paused here and tried to do the next couple. Okay, welcome back. So I've calculated for you the probability of getting 2 Skittles, of getting 3 Skittles, of getting 4 Skittles, 5, and 6, and so on. And I've also plotted the bars of the histogram to the correct height. Check your work against this, and we'll go on to the next problem. Okay, so this next example looks back at the example we just did and asks the question, what is the most likely outcome on the histogram that we just made in example 2? So let's look back. Alright, here's the histogram we just made. Which has the highest bar? That's the most likely outcome. So 2, getting 2 red Skittles produces the highest bar, and that bar has a probability of 0.32 associated with it. And this makes sense, actually. So because we did this 6 times, and the likelihood of getting a Skittle that is red is 30%, then the most likely number of Skittles we get that are red out of 6 is 30% of 6, which, if you do that, is approximately 2. It's a little less than 2, but it's approximately 2. And so that's why 2 has the highest probability, the highest bar here. What is the likelihood of getting at least one red Skittle? Well, again, let's go back to this thing. We could say, okay, at least one red Skittle, so that's the probability of getting one red Skittle, that's this guy here, and plus the probability of getting 2, plus the probability of getting 3, plus blah blah blah. We could add all those up except for the 0 one, and that would give us the probability of getting at least one. Or we could take the less work route and realize that the probability of getting at least one red Skittle is the probability of the complement of getting no red Skittles. So really, this is 1 minus the probability of having 0 Skittles appear. Okay, well what is that probability? When k is 0, that's this one, we got 0.118 as our probability out. So 1 minus 0.118 is equal to 0.882. Alright, so in this video you learned what a random variable is, what probability distribution is, and how to interpret a probability distribution. You also learned what a probability histogram is and how to interpret one. And finally, you learned about a specific kind of probability distribution, the binomial distribution. See you all in class.